We will first start with a motivation example for higher order ODEs. So motivation. Example for higher order ODE. And that is from a system called mass spring damping. System. And we are trying to derive here a second order ODE as an example. So we have a spring. The initial status is a spring with a mass here. So the original, as a references, the original spring with the length is this much. So we refer this distance as 0 equals to 0. After it's connected with a mass subject, the length of the spring will be changed. So the change part referred to the original spring will be as 0 with a negative number there. And this is the static status. Means after it's connect with this mass, it's already reached its own equilibrium, false equilibrium. So for this subject, it's for this subject, it has two forces. One is the gravity, which is mg. The other is the mass spring, which is minus k as 0. The k is the spring constant. So if you write as force balance for the subject, we can write minus k as 0 minus mg is equals to 0. So that is our equation 1. Then another system we can consider, what if that is now static status? What if it's already have some motions? So what if it's not as 0? It's actually, this is still the same subject with mass m. And instead of as 0, it's actually add some more forces here, which is S0 plus X. So it's adding more force to make this subject to move. It still have the gravities. So after that, we add basically acceleration part by this X length of the spring. We can write this system as K at 0 plus X minus mg equals to ma. So the a is the acceleration of the subject. And you also know that this a is basically the second order of the distance. And we can also write as double dot here. Okay, probably not clear. So double dot of the x. And then you can rewrite this form as minus k as 0 minus kx minus mg equals ma. And that a is the m double dot. And you know the minus k as 0 minus mg equals to 0. Then you can get the final equation is minus kx equals m double dot. And this double dot is the second order of the x as function of t. So this is a higher order ODE, which is the second order ODE. We can even add a damping system, so a damping force. A damping force, which this D represent by damping. This damping force is proportional. It's proportional to the velocity. And you know this velocity is the first order of the distance, which is x, represented by the x dot. So we can even add a damping force m here, and it can be S0 plus X, and there is mg. There is also a damper force, Fd. So in the end, the way you can write is minus K S0 plus X minus mg minus Cx, which is represented by the damping force. That is equals to ma. And you can rewrite these equations minus k s0 minus kx minus mg minus cx dot equals ma is the x double dot. Then in the end, this part minus ks0 minus mg, that is equals to 0. So you can get the final equation is minus kx minus cx dot equals to mx double dot. So after the damping, it's still a second order ODE. And it is a linear ODE because this K, C, and M is basically either constant or only as function or for the spring only. So we can treat it as a constant. When the coefficient is only constant, this is a linear second order ODE. Okay.